All right. So now why does this actually occur? Why does this happen? Well, the concept is something that we want to call a microstate. Okay, what's up with a microstate?
Well, this has to do with statistics. Where are the molecules, in this case, we're going to have some gases in here, where are they most likely to be most of the time? Are they like, if we have two chambers here, and in one side is a gas and the other side is completely sealed off, it's a vacuum, and then we open up that little stopcock in the middle, where are they what's most likely going to happen? Are they all going to stay in one side, or when this reaches an equilibrium, are they going to be evenly distributed throughout?
A, B, C, D. Actually,
okay.
That's what I want to do. So if I've got chemical A, and they could all be the same, but we'll kind of put a little tag on it, A, B, C, and D on this side, and we open up the valve, what you're going to get are some different options. Hold on, I'm trying to, my stupid program. Okay, there we go. This is what I want. So let's think about this. We've got our two chambers here. All right, so we've got chamber, well, let's just say the left side and the right side, right? So let's, let me change colors here. All right, so on the left side, we could have A, B, C, and D. That didn't go very well. Oh, well. That's one option. What's another option, Mr. Sams?
We could have A, B, C on the left. Oh, and D on the right.
Oh, okay, good. I see that.
Okay.
Any other options?
I could do A, B on the left, C, D on the right. I could do A, C on the left and B, D on the right. Let's see what else. Let's go A on the left, B, C, D on the right. Okay, then we could go B, C on. Okay, we can go B on the left and A, C, D on the right.
And then we can go C on the left.
And A, B, D.
A, B, D.
D on the left.
And I can go D on the left and A, B, C. And of course, you could take these right here and essentially flip them.
Yep.
So there would be three more options where we have B, C, D, A, C, D, A, B, D, A, B, C, and this is A, B, C, D. Now let's do the two twos, Mr.
Yeah, the
Sams.
two twos, there's quite a few of these.
So we've got A, B, C, D, A, C. So let's think this through here.
So we could flip those if you wanted to.
Yeah,
or
so
we could just start with the B's, whatever you want to do.
Let's do the B's.
Okay, so we could go B, C on the left and A, D on the right. You could go B, D on the left and A, C on the right. And then we could go
C,
we already did,
D.
yep, C, D on the left and A, B on the right. And I think any other permutation is going to be a repeat of any of those, just in different order. AB versus BA type of thing. Yeah.
And then, of course, we can have 0 on this side and A, B, C, D on the left. Now, the whole point of this is it's actually just this statistical option. Basically, you can either go 1 and 3, you can go 2 and 2, you can go 1 and 3, or 3 and 1.
You already did 1 and 3 at the top.
Oh, this is 3 and 1, sorry.
Then we could do 4s and 0s.
And then we can do 4 and 0.
Or 0
or
and 4.
0 and 4.
Yep.
Now what you do is you actually tally these up.
Yeah, and I think we actually missed a few or repeated a few or something.
I think we did.
Yeah. Anyhow, not comprehensive list, but you'll get the idea.
You get the idea. Here's the point is if you were to do the statistical math, and I don't think we've done it right, you're going to get a lot more that fit this category.
The 2 and 2.
The 2 and 2.
Yep.
And then the 1 and the 3, you know, you'll get quite a few. Or the 3 and the 1, it's the same number. And the 0 and the 4, you're only going to get one different possibility.
Yep.
Now, this is only with 4 molecules of gas in our substance. If we jump to, say, a mole of gases, so if I had just a jillion, 1 mole of gases in here, then this number would become, essentially what's going to happen is it's going to go 50% and 50%.
Yeah, and that's going to be the most statistically favorable position.
So, and that's called a microstate. So the microstate that's most favored is the one that's most spread apart.
Yeah, it's also called positional probability. Where is it most likely to be positioned?
And so that's how we can understand why things spread out. This is kind of why do things go from order to disorder, because it is statistically the most probable arrangement. So that is basically the concept, and yeah, I think we're good on that.
Okay.
Possible arrangements, we did that on the other page. Okay. Now, we should talk a little bit about some laws.
Yep.
Thermodynamics actually has several laws. There's, you've learned the law of gravity, and what's another law in science? Newtonian laws of motion. First law of Newton's first law, and second law, and third law.
Yep.
Well, there's also thermodynamic laws.
Yep.
Okay, and there's three laws: the first, the second, the third law of thermodynamics. The first law is called the law of conservation of energy.
Right.
What's that?
You can't create or destroy energy. The amount of energy is constant. You can transfer its form, but you cannot create or destroy the energy. Now, this is a little sketchy when you get down to the nuclear level, but as far as chemical terms goes, this works.
So you can't create or destroy energy. You can only change its form.
Right.
So, for example, when you drink that coffee in the morning and you have
my
that
sugar in there, that's got chemical energy, or it's got energy stored as potential energy in the chemical bonds of the sugar.
And then, of course, when you eat it, or drink it, I should say, and whatever.
It goes into my body breaks it down, it turns it into other forms of energy. It pretty much transfers it into heat energy that my body gives off, and then another form of chemical energy.
Or possibly mechanical energy,
as you
move
energy
your body,
as
you run or walk or whatever.
Exactly. And then I can do stuff. I can lift a chair up, or I was going to say lift weights, but I don't really do that. So
I lifted weights this morning.
Oh, yeah? I slept in this morning.
Yeah. Actually, I slept in a little bit. I was going to ride my bike, but I'll do this afternoon.
Yeah.
And I know it's snowing. I'll ride it on a trainer because it's snow and ice out there. Okay. Another important thing to understand about heat, it always flows in one direction. It can never, ever go
or higher heat to lower heat. There's really no such thing as cold. It's just less heat.
So, yeah, good point, yeah. And so maybe you've probably heard this story, but if you have your house and it's a cold day, like it is right now outside where we live.
A less warm day than usual.
A less warm day. And you open the door and your mama says,
"You're letting the cold in.
You're letting all that cold air in. Would you please shut the door?" Now, with great politeness.
Mother.
And with respect. You need to inform her that she's...
Yes, Mom, we are not in fact letting the cold in. We're letting the heat out.
You can never let the cold in.
Don't sass your mama.
But don't sass your mama. If you sass your mama, you got to answer to me. And I lift weights. Okay. My voice is going away, though. That's not good. All right. Second law. What's the second law? Systems that have an overall tendency to...
increase the entropy. That means they're getting more disordered. We talked about that a little while ago.
Yeah, so we have discussed this already, I think. So we need to... This is a couple of examples, of course. Mr. Sam's talked about his desk getting more disordered. Possibly, just think about, ladies and gentlemen, your room.
Yeah.
You probably have a room you live in. You've got your bedroom, and my guess is it's a disaster if you're like any teenager I know. And I have a teenager at home. And so the room has become a disaster. And it doesn't take, if you don't put the energy into it, it becomes a disaster. And you know it's true, etc. But that's also true of that cube of sugar. When you take that cube of sugar, you drop it into some coffee or some water, whatever, it breaks apart into many, it gets spread apart and becomes an aqueous substance. And that is also a demonstration of the second law of thermodynamics.
Yeah.
Okay.
So actually in the Sumdahl book, they sum it up really nicely in the back of the book. They say the first law of thermodynamics says you can't win, you can only break even. That's the law of conservation of energy.
I like that.
And then the second law is you can't break even. Because it's always going to go to more disorder, and you're going to have to put more energy back into the system to get it back the way it was.
There you go.
So it's kind of like Murphy's law of thermodynamics.
Yeah. Now, hey, free energy.
All right. I like this stuff. I like free energy.
It's so cool. Free. It's free. It
is.
Cost anything.
I like free stuff.
Actually, free energy is an interesting thing in terms of its definition. It's the amount of energy available. How do I say this?
Yeah, available to do work.
Yeah. I think I misspelled that. Oh, well. To do work. So it's the amount of energy that's sort of freed up to do stuff.
Yeah.
So, yeah. Now, there's like this, in thermodynamic world, there is like this uber important equation.
Yes.
If you don't get anything out of this equation, well, there's two important concepts here to understand today. But this equation, delta G is equal to delta H
minus
T delta
S.
So actually, it's really a function, delta G. And free energy, by the way, did we say this? Oh, free energy is delta G.
Yeah.
Equals...
It's sometimes called Gibbs free energy. That's where the G comes from.
Yeah. Let's write that down, Gibbs. Some dead white guy, I think, was Mr. Gibbs. And so delta G is actually a function of delta H and delta S. Remember, delta H is that enthalpy. And delta S is what we were just talking about just a minute ago.
Entropy.
Entropy.
What's T, Mr. Bergmann?
And what is T? T, of course, is the Kelvin temperature.
Must be Kelvin.
If you convert it in Celsius, you're wrong.
Yep.
Don't do that, please.
Nope.
You must work in kelvins. And so you must always have that going for you, otherwise you're host. And so basically you can calculate delta G based upon the other two. So, yeah. The fundamental properties are things that matter in the world are the delta H and the delta S. But the delta G is then how you kind of smoosh them together, I guess, is the way to think of it. And there's an equation, mathematical, so if we knew a value, knew a number for delta H and a number for delta S, then we could solve the problem. Now, probably